In the last video, we saw how there could be an industry that has two firms, a duopoly, and if those two firms coordinate, they could behave as a monopolist, and they could optimize their collective economic profit. And in the last video, we saw that would happen when they produced 50 units per period, and they could split it, assuming they were two identical firms, by each producing half of it. In the case of the last video, it was 250 units per firm. But then we saw that there was an incentive to cheat. That by producing extra units, the margin, from a market's point of view, the marginal economic or the economic profit on those incremental units would be negative. So the whole economic profit would shrink a little bit as you produce units beyond that. But the cheater would get a bigger chunk of those units, or the bigger chunk of that economic profit. And so the cheater could actually gain, go from $250 per time period to $280. And it would be all at the expense of the non-cheater, who and then some, who would lose even more than what the cheater gained. And obviously, who was initially the non-cheater has an incentive now to cheat, and they'll both keep increasing. They'll both keep increasing production, so that if they wanted to keep doing this one-upsmanship, and so they both have the incentive to keep going, assuming that they don't hold to their cartel agreement until you get to a quantity, where there's no economic profit left. So right over here, the way I've drawn it, the demand curve intersects the average total cost curve right over here, and there's no economic profit left. We're producing a good quantity. It looks like it's about 75 units combined, 75 units for the whole market. But at this point, the market price is equal to the average total cost, and so there's no economic profit per unit on average. And what I want to do is think about this in kind of a game theoretic way. So let's look at a bunch of states. And so this is the optimal state that we are starting off in. And you can actually call it the Pareto optimal state. Pareto optimal state, named after Vilfredo Pareto. And all it means is that's the state where there's no other state where you can make someone better off without making the other person worse off. So any of the states here, there are states, for example, where blue is better off. So for example, in this state right over here, blue is better off, but green is worse off. So that's why it's called Pareto optimality. Now, what I want to think about is how these characters will change their state due to their incentives. And then we'll talk a little bit about Nash equilibrium as well. So on this axis, up here, let's say that this is one of the competitors. This is where they produce 25. And let's say on the ultimate cheating quantity of 75, and this is somewhat close to kind of the market, or that is the equilibrium quantity if this was perfect competition, they produce half of that. So this is them producing 37.5 units. And as we go from 25 to 37.5 units, they are cheating more. So this is more cheating, and over here, this was no cheating. And we can do the same thing for the blue player, and I'll write them as B. This is them producing 25. This is them producing 37.5. And as we go up and up and up, they are cheating more. So this is a lot of cheating, or more cheating. So to think of it in a game theoretical way, this is the Pareto optimal state right over here. And it's optimal in many ways. They've maximized the total economic profit here. There's no other state that one person would benefit without making the other worse. Now, let's think about whether this is a Nash equilibrium. So let's remind ourselves what Nash equilibrium was. This was a state where holding all the other players constant, so in this case there's only one other player, holding others constant, a player can't gain by changing strategy. Player can't gain by changing strategy. In this case, changing strategy is changing your output by changing strategy. So let's see if that is true of this state right over here. Well, let's hold A constant. If A is constant, we're in this column right over here. Is there something B can do? Is there change of strategy B can do that would allow B to gain? Well, sure, B can increase production. That's what we saw in the last video. So we would go from this bottom right state to one right above it. Now B's economic profit is 280, A's is 200. The pie has shrunk, but B has got a larger chunk of it. So that was not a Nash equilibrium. There is holding all others constant, there is a player that can gain by changing their strategy. And this is by holding the Nash equilibrium definition, just to make sure. They say it's a state where holding others constant, no player can gain by changing strategy. We just showed that at least one player can gain by changing strategy, holding others constant. And the same would be true if we went the other way around. If we held B constant at 25, A could gain by changing his strategy. Could go right over there. So this is not a Nash equilibrium. So this is not a Nash equilibrium. And then regardless of what state we go to, if we go to this state, it's still not a Nash equilibrium. If we hold A constant, B can improve by increasing his production. Or if we hold B constant, then A can still improve by cheating even more. So none of these are Nash equilibriums. From any one of these states, if you hold A constant, B could produce more, or if you hold B constant, A could produce more and get some gain. Over here, A is going from 130 to 160 and getting some gain. And you can imagine this keeps happening incrementally. They keep producing more and more and more. We kind of go there, then we go there, then maybe we go there, then we go there. Then maybe A cheats some more, then B cheats some more, then A cheats a little bit more, B cheats a little bit more, maybe a little bit more past that, then A cheats a little bit more. The whole time, the whole economic profit pie, which is the sum of A and B, gets getting smaller and smaller until finally A finally cheats, and they are at zero economic profit. Now let's think about whether this is a Nash equilibrium. Clearly, they won't want to move backwards. If you hold A constant, B would not want to move down. Then he would lose economic profit. So that doesn't work. He doesn't gain by doing that. And if you hold B constant, A wouldn't want to move to the right. A would also lose economic profit. Now you might say, well, what if they produced beyond 37.5? Why can't they keep producing and go beyond there? Well, if B holding A constant, if B were to produce more than 37.5 from this state right over here, then the total pie will get negative. And it doesn't matter if B's getting a larger or smaller chunk of that pie, B's chunk is going to be negative. He's going to drive down the price even more. And you can see it over here. If they increase quantity beyond this market quantity of 75, 37.5 each, if we go beyond that, the price that they would be selling at that quantity over there is lower than the average total cost. And so you're going to be the average economic profit per unit is going to be negative. There will be a total of negative economic profit. So neither of them will want to produce more from this state either. So all of a sudden in this top left state, holding others constant, B, if you hold A constant, B can't gain by changing his strategy. And if you hold B constant, A can't gain by changing his strategy. And so we are up here in a Nash equilibrium. This is a Nash equilibrium. And like the prisoner's dilemma, equilibrium. It was not the optimal state. The optimal state was here, but because they both wanted to cheat, they both wanted to do this one-upsmanship, they both broke their contracts, they could end up in this state over here. But this state is stable. There's nothing holding the other party equal. There's nothing that they could do to change, to optimize. Now, what they could do, and this is not what Nash applies to, they could say, okay, we've been really ruining each other's business. Let's go coordinate again, and I'm going to decrease production if you decrease production. Now, that is not, and they could maybe try to go back to this state, and that does not mean that this is not a Nash equilibrium. Because by coordinating again, we're not holding the others constant. We're saying, I'm changing my strategy while you're changing your strategy. And so maybe only through another agreement they could go over here. But that still doesn't mean that this is not a Nash equilibrium. This is a Nash equilibrium. If there's no coordination, if you hold one player constant, the other player cannot change their strategy or change their production for a gain.